Okay, hello. My name is Rubik Sheth. I'm from the Johnson Space Center. I work active thermal control. Thermal is thermal, right? But we like to put them in somewhat of a box where we call it passive, active, or cryogenic thermal control. But we're here to talk about thermal systems and just lunar environments in general and how they impact thermal architectures. I would like to reiterate what Andy said, where it's really important when it comes to thermal, not only to talk about thermal solutions, but to talk about vehicle level solutions that allow for thermal distribution, right? So you take advantage of waste energy from various locations to help warm or cool whatever's needed in other areas. And so we set up a panel, a really good panel, to help talk about how it's been done in the past, take some lessons learned into account, and also talk about some of the thermal environments that drive us right off the top. So first, just some ground rules on the panel discussion. It's like I said, a quick overview of just our thermal environments that drive us. It'll be it'll hit the high level stuff. This morning, I think Brett did a really good job of discussing some of the specifics about thermal environments and the issues on the lunar surface. I'll have very few lessons learned from the Apollo era, and then even some international orbiting satellites, and then some design considerations as discussed by the panel members. But I really want to press on the open discussion. We want it to be not to talk about what we have experienced through whatever research or vehicle architecture trades we've done in the past, but really talk about some out-of-the-box solutions or out-of-the-box ideas that maybe the audience could come forward with. So I will be specifically talking about the thermal environments, again at a very high level. Eric Sunada from JPL will bring in a robotic spacecraft perspective. He has led a lot of robotic spacecraft work out of JPL regarding the Mars missions and now the Europa Clipper mission. We have Chad Bauer from industry. He is from Paragon Space Development Corporation, and he'll be talking about the industry perspectives on thermal management when it comes to commercialization. And finally, Kurt Sackleader, he's from Glenn Research Center, and he'll be talking specifically about the thermal wadi, which you guys heard a little bit about this morning through some comments. So jumping right into it, so we've been talking, I like how we've been talking a lot about lunar surface ops, but to get to the moon, you have to orbit the moon a little bit. And when you orbit the moon, there is still a very harsh lunar environment, right? And so I'll go through lessons learned on the next slide, but before you land on the moon, you have to design to potentially orbit above the subsolar point of the moon. And that is one of the warmest environments that an orbiting satellite it absolutely would see for the moon. One of the points in case for Orion right now, they're in the process of developing their vehicle to orbit the moon. That's that new crew capsule that's based off of an Apollo-like look, but on steroids, as they call it. They had the same issues with lunar orbit, and through STMD, we were able to go fund some phase change material heat exchanger work to help work as a thermal capacitor for the vehicle as it would orbit and go through those cyclical environments of hot, cold, and hot, cold. And so, like I said, we talked about the surface environments, but right before you get to the surface, you have to orbit the moon, and that's one of the design considerations that any vehicle will have to take into account when going through their entire mission profile. As we saw this morning, planetary albedo is very low, which means that the surface is essentially like black paint. It absorbs everything it gets from the sun and then re-radiates it back to that vehicle that's on the surface. That diminishes as a cosine function from the subsolar point. Again, as we saw through some of the plots from LRO, from the flight vehicle itself. And then finally, I pulled this from one of my esteemed colleagues that's sitting in the audience, Jeff Farmer, one of his papers in the 90s where he did an empirical analysis to really understand what the lunar surface temperatures were based off of what latitude you're at, from the subsolar point all the way down to the poles. And again, you could see it's just the same thing, right? You have large variations as you move from the equator out to the poles. And if you're looking for global access for your lander or for your rover, you have to design for each one of those bands. And that becomes a very tough thermal solution on top of just surviving the lunar day-night cycles. And so what does that mean? What have we seen in the past? like I said, lunar orbit, it really did wreak havoc on the Apollo missions. From what I've heard and collected data from, on the Apollo vehicle, when they were orbiting the moon, they actually used something called a wick evaporator to help manage those peak loads at the subsolar point. Well, that wick evaporator actually froze over and did not operate as intended during the first initial missions. And what we found was the crew would come back with colds because they would go through multiple internal vehicle temperature fluctuation from 90 degrees Fahrenheit all the way down to 60 degrees Fahrenheit over a 2-hour span. And that would happen for a day on end. And so they'd come back with a really bad cold, and that's because the lunar environment really influenced the internal cabin temperatures. Another scenario, but for a satellite, the Indian Space Agency launched a satellite, an orbiting platform, much like LRO, that actually, I think it was in 2008, where it actually failed a day into orbit because it was going over the subsolar point, and the vehicle temperatures raised more than 50 degrees Celsius, causing instrumentation needing to be turned off, the attitude of the vehicle being changed. It just took away from its capability, and essentially it was, the mission was a loss in the long run. Looking at the surface, Apollo surface operations, an interesting note, right? We talked about craters, but there's also hills and mountains on the not mountains, but at least hills on the lunar surface, and they actually have a pretty big influence on that environment as well, right? So that IR backload off the lunar surface going to the moon has caused, or going back to the vehicle, has caused temperature increases of at least 10 degrees Celsius. And that matters when we're talking about tight temperature control for instrumentation science programs. Lunar dust has been talked about as well in the previous talks. We've heard a little bit about that. One thing to talk about there is there's two things, right? Lunar dust increases your IR, your absorptivity, your solar absorptivity of the sun's impact on the surface, but it also is a poor conductor. It's an insulator, the lunar dust. And so if you think about it, if you have all this dust on your rovers, as you see in the picture on the top right, you almost are insulating your entire vehicle. So then when you go into a colder environment, you're causing your vehicle to reduce in temperature, and now it's going to be at this reduced temperature for a little bit longer period, and stay that way because you're insulating it. And so now you have to design your materials around withstanding that temperature variation, and then withstanding that low conductivity to help modulate that temperature on the material side. So quick lessons learned. I didn't want to dwell too much on it because we had talked about it this morning, but yeah, those are some of the impacts from the lunar environment, and then the associated lessons learned from that. Next, I'll jump right into, I think Eric's going to talk a little bit about JPL and how JPL has, thermal architectures have influenced JPL's robotic missions.
Thanks, Ruvik. At JPL, we've been focusing mostly on the near term of science that looks at the environment or interior that requires operation both during the day and night. So we're looking at distributed networks, trying to leverage the opportunities that some of these commercial managers may provide us. These are just some of the things that we go through in designing for those cases. First, of course, make yourself warm, survive the night. Decoupling from the environment, that's because we do operate during the day, so we want to minimize the radiator size and also to save light, whether that's done with a device such as a heat switch or an active cover. And also, to give you an idea of the types of energy balance that we're talking about for our smaller distributed network, we're chasing less than a watt. We're chasing hundreds of milliwatts sometimes. So it turns out that the insulation is one of the largest leaks that we have, and getting really effective MLI that tolerates dust and get down to less than 1% through it is key. You know, the other rule of thumb in general is that, you know, we want to gather a mass of similar temperatures requirements together to help grind out the transient. Granted, the transients are half a month long, but it helps nonetheless. And then, of course, barring that we have cold capable electronics, you know, we're going to have to bring a heater. And so, near term, we always turn to chemical batteries, whether it's a secondary battery, where we have like 150 watt-hours per kilogram, or some of the more advanced primary batteries that are around 250 watt-hours per kilogram at the battery level. So we work a lot with the power folks, as was mentioned earlier, and it's you know, it's a constant trade there. Of course, you know, as mentioned, if we had radioisotope power, that is something that, again, it is an enabling feature. It gets us to be able to survive the night. We've done these things. JPL, we've done it on Mars. The other one's also with RTGs and reclaiming the waste heat. So, you know, a lot of times on our spacecraft level, we just take what I call the high quality heat in the RTG that's often at 200C, and just radiate within a cavity. The Curiosity rover, we're actually using a single-phase loop to gather waste heat and bring it back to the electronics during the night. And some of the, you know, really low TRL far out there type things is, you know, combustion. If you had extra propellant, hydrogen, oxygen, microcombustors to provide heat. So it's something kind of wild out there. And the next rule of thumb is, you know, find shelter. So with our rovers, the idea is to, you can't afford to have the actuator to cover your radiator, or decouple it. Maybe you can drive to shelter, or take advantage of a lander, or a parking garage that can house several small landers. And also going into lunar features like a pit. Building your own infrastructure, the wadis that we heard about here, and also you just brave the cold, and of course low temperature electronics helps. One of the things that we are looking at lately is the trades of distributed network for environment and environmental studies. And on Mars, we were able to do that. We had a passive rover with RHUs. We used heat switches. But the lunar environment, the diurnal, is so much more extreme that that technology would not work with heat switch. So, you know, we did trade studies, and we needed a heat switch that operated about, I'd say, 4 times as good as the one that we used on Mars. And so lately I just have to show that, you know, one of the things that we've been focusing on is an advanced heat switch. That there's a poster over here, you get more details, data pumping, it can do a turn down ratio of 25 liter to 1 as compared to Mars, which is over a order of magnitude less performant. So this is something that can enable us to close on a design with batteries at this type of users.
Okay, so next will be Chad to talk about the industry perspectives.
Hey there, I'm Chad Bauer. I'm Paragon's lead thermal engineer. And I've thrown up some pretty pictures. And I'm not going to talk to you about any of them. Nor am I really even going to talk to you about thermal control technology. And there's a couple of reasons for that. One is because I was invited to talk about commercial aspects, and I think that's important to stay focused on. I'd like to hear your comments on it. But let me give you a little bit of background to tell you why I did put up these pretty pictures. Paragon's been around now for 25 years in the pursuit of development of commercial life support systems. We like to say that when you go to the moon someday or Mars, that you're going to step off of a vehicle and across the door it'll say life support brought to you by Paragon. That would be great for us. But we've been doing this for 25 years now, and I can't say that we're a commercial company. We don't do commerce, we do contracts. All of these things on this that we've made many CAD figures of and many products of as well. They're all essentially one-off designs. Most of the systems that we have built kind of goes along the NASA adage of how they procure and use things. I heard this recently, and somebody correct me if I get it wrong. NASA buys 5 of a thing. It's one to break, one to bake, one to shake, one to fly, and one to put on the shelf. And in general, that's what we've done. Now, as NASA has moved us in a direction of utilizing truly commercial partnerships. Of course, SpaceX is a great example. We've got one here with SNC, who we're partnered with. The unit size here is starting to move us in the direction of commercial space. Commercial space is really going to have to get to a commodity level if we're ever going to call it commercial space. I'll give you an example here. For, Ruby, you want to hit the next slide there? Up in the top left is a very simple, ubiquitous thermal control solution and an air conditioning system. And around that small picture is a plot of the population of Phoenix, Arizona. You probably can't read the bottom there, but that's from 18 commodity level air conditioning systems. And it's that level of utilized technology, and I call it utilized, but it's not emerging technology. It's that utilized technology in a commodity form that has enabled people to move into extreme environments. And we're talking about one of the most challenging extreme environments known to man. We have to solve the problem of going there, of operating there, and we have to do it continuously, and we have to do it on the cheap. I've heard lots of the huge technological challenges that are involved with getting to the moon, staying on the moon. I hear about power, I hear about dust mitigation, another extreme environment challenge. Thermal has its own very large problem to solve. But I think something different about thermal in comparison to some of these other technologies. For thermal, the technology almost in whole already exists. In general, when we talk about solving a thermal challenge in engineering, thermal comes in, and I like to say, we come in as the redheaded stepchildren of engineering. There's a problem, it needs to be cooled, it needs to be heated, thermal guy, come fix my problem. And there is now a repository of these thermal control solutions that are applicable on the ground and in space that, as a commercial technologist, we understand we need to identify and find ways to make systems that are largely modular, that identify and solve scales of problem, and that use technologies that currently exist. Now, the moon is an interesting location because it's sort of missing one of those classic modes of thermal transport. You get in your car, you turn on this giant beast of a power plant, and it creates an incredible amount of heat. And we just blow air over it, it goes away. We don't have any of that in space, right? We're dependent on radiation as both our source of energy and our way to reject that energy. But the solutions, the physics for these problems are well known and can be applied. The challenge is really at the systems level, and I'm sure you can tell us all about the types of systems level solutions that solve these problems. And again, I'm not going to tell you about any of them. There's the solutions for short-term or short distance conduction, for moving things over larger distances and heat pipes, or pump fluid loops. All these things exist. There are various levels of maturity, and they need to be assembled at the correct scale to do the job. But the great thing about the moon, for a thermal problem, is that we have all the physics available here. We don't need to have a laboratory on ISS to figure this out. We can develop a cold chamber. We can generate these standardized systems. And I say standardization, I've heard that a lot of times today because I see that as NASA's role in preparing commerce for success. Again, we did see that in terms of folks like SpaceX and SMC. NASA's role is now to, the exploration has occurred. We've done basic exploration of the moon. When we go back, we have to do this in a commercial manner to make it make sense. We can do science on the back end of developing that commerce, or allow some science to bring us to the point where commerce makes sense. But we're going to need commerce to make sense for staying in this region for a long term. So again, I really see NASA's role going forward as taking these lessons learned, generating the standards that are necessary, in allowing industry to do its thing, and I think it will. So with that, I leave that to the open panel for more discussion, and that's his open.
Thank you, Chad.
You can flip view Brett for me when you.
Yeah, absolutely. Yep. So
Okay.
now it's thermal wadi.
All right, so I was given instructions by the organizers to keep this short, and that's sometimes tough for me to do. There are many more things to convey on this subject than I can do here. So I tried to identify a few high points here. All of the concepts I'm going to talk about here, and I'm not even including a lot of quantitative data, but that data is available. All of this work is based on a lot of pretty detailed numerical modeling, but a lot of it was also backed up with some experimental work to kind of, keep the modeling relatively honest. There's a lot more that could be done in both cases. I have a couple of names up there of folks who have participated in this work over the years. A lot of this was done like between 2012 and 2010 to 12 or so. So it's been around for a while, and we haven't been able to do too much with it since then. So next slide, please. What underlies this was early thinking in the ISRU community that while it would be nice to go to a particular location and prove, yes, we have water ice right here, to really get a handle on the resource potential of the moon, you really needed to be able to map where these potential resources were over, perhaps even a regional scale topography. In order to do that, you had to have mobile assets that would move around. And clearly, one of the first things that we thought of was that no matter where you were on the moon, either equatorial or polar, that there were going to be thermal issues. And we realized in looking at what you had to put on a rover to have it survive the night was that a big part of the mass that you have on a rover is some kind of energy source or storage device to carry that energy around with you and then consume it during the night. So our thought really came down to we need to think of a way to offload that energy source or storage requirement, hopefully to a simple architecture that these mobile assets could take advantage of. So that's really a very simplistic summary of the background here. Now, so the idea for the thermal wadis, and I will mention, I told my co-panelists here that the word wadi was misused from the very beginning of this, but it's a catchy word, so it continued to be used. But the idea is to use solar thermal energy to heat lunar regolith and store energy in it during the night. Now the problem is that The loose, dusty regolith has a really horrible thermal diffusivity, makes it a great insulator, but a really terrible medium for storing thermal energy. So our solution was that you simply have to consolidate it in some fashion. There's many possible ways to do this. You can melt it using concentrated solar energy. You can use thermite reactions. You could even mix it with other materials that you brought from Earth, but in some way consolidate it so the thermal diffusivity would be increased. If you melt the native regolith and re-solidify it, you increase the thermal diffusivity by about 2 orders of magnitude, so you really improve things quite a bit. So let me see what I wrote on my charts here. So we improve the thermal diffusivity, and then you've created a thermal mass, and in some fashion you use either just ambient solar irradiation of the surface, or you can improve on that quite a bit if you actually are able to steer reflected solar irradiance onto the material. If you do that, and this is the result of a lot of detailed thermal modeling, if you only need a 50 centimeter thick slab, and if you by square meter or whatever, but 50 centimeters is deep enough so that during a 14-day period you can heat it up to a surface, can be kept to about the vicinity of the boiling point of water, and you can keep it, it stays warm enough overnight so that it doesn't go below the freezing point of water. So you have that temperature range. It requires that you very carefully shield the surface from radiated losses during the night, because that will wipe it out pretty quickly. So the sun tracking actually, I think, really enables that 50 centimeter thickness. And sun tracking would be critical if you're going to employ this technique near the poles, of course, because if the sun does not go overhead, it wouldn't work very well at all. So one approach to creating these thermal masses would be simply to use concentrated solar power to melt the regolith material. We've demonstrated this, and other labs have done this too. There's a lab at Goddard that did this as well. You can clearly melt enough mass of the regolith to create a 50 centimeter thick slab during 14 days. One of the studies that we did was of the optical properties of these surfaces, and it turns out that a thin layer of dust on the surface actually helps. It tends to suppress the radiative loss if you have it. So that's actually, probably the first and only thing that will be said during this entire meeting good about the dust on the surface. So next slide, please. So that's kind of the general concept, but we wanted to talk a little bit about how you would utilize thermal mass that has been used to store solar thermal energy. So we did some studies to look at the design of small mobile devices that were particularly engineered to be able to interface with these thermal masses. So you've got to design, the underside of a rover to be able to somehow couple to that thermal mass. It can be conductive, it can even be radiative, but you have to pay attention to the fact that when it's not sitting on this mass and it's driving around during the day, it's going to be interacting with a very hot surface. And so these rovers have to be designed to not be absorbing heat during the daylight hours. So there's some design challenges that are there. But if you design the vehicles to interact with this thermal mass over the course of a 14-day, and you limit the heating requirement of that vehicle to about 25 watts, these thermal masses can provide that 25 watts throughout the lunar night. So we looked at a variety of different ways to do that. I'm not going to go into all of them now. There's some papers, and we can talk about it afterwards. But you can even have, some rovers that basically drive around and they make new thermal bodies. And so, during the course of one lunar day, they can produce another thermal mass, perhaps, a kilometer away from the last one. So there's a way to gradually build a network of these sites around the lunar surface. And there's other potential uses for this stored thermal energy. We did not go into too much detail, but I think the last time I attended a league meeting, I actually showed this, and someone took me up on this and did an analysis that if you create a thermal mass that you heat with incident solar energy, and half a meter away you create another thermal mass, and you arrange it so it becomes a locally permanently shadowed region. It's sunk a little bit below, so it's only radiating to space. You can have a very cold thermal mass in proximity to a very warm thermal mass. And for all of you that took thermodynamics, you can stick a heat engine in between those two and generate electricity whenever those two things have a sufficiently different temperature. So a little bit of analysis shows that this is a concept that would be relatively impervious to any difficulties with the lunar dust, which is a little different than other solar power generating devices. So there's other ways you can use these thermal masses. So the idea here, and I'll just finish with a repeat of the comment I made. I think one of the approaches to doing resource assessment and scientific measurements around the surface of the moon is to have mobile assets, and those mobile assets have to survive, and this is a way to do it. And the principle is to offload a lot of the energy requirements from those mobile devices to a simple surface infrastructure. So that's all I had to say, and I think we're ready to dive into some questions and discussion. Thank you.
Yeah, so I think that wraps up the panel discussion part, but want to reiterate that it's thermal isn't just a self-thermal issue, right? It's a vehicle level issue that needs an integrated solution, which is what Chad and Kurt and Eric tried to talk about there. It's perfectly understandable that we looked at other maybe power systems, right, and then take those power systems and create thermal design solutions around them. But really, we got to look at it as a vehicle architecture rather than just a specific component and help distribute that load. So, without too much more, I'd like to open it up to discussions. Any questions that anyone has? And there's more cookies outside if no one does.
I have a question. The paper that you talked about with the sintered blocks, was that done on a large scale, as in enough to drive an actual road ramp? Has anybody done that in a sized up, full scale?
No.
Mike.
Michael, right.
So no, that's expensive.
And who's going to write the check?
Well, we have to, for that to be meaningful, it needs to be done, in a vacuum chamber that can be thermally controlled as well, and that you can have dirt in, and that's a challenge. But what we have done is to use concentrated, sunlight during a summertime experiment in Cleveland, Ohio. Like a half-meter diameter solar concentrator, and it pretty readily melts, a half-centimeter dot of material, and you can, raster this back and forth and sweep similar dirt on it. We had a setup ready to go to do the same experiment in a vacuum vessel that had the dirt in it, but not have the whole system in a vacuum vessel. So that's much cheaper to do. You just have a little container with a window on it. And so I'm quite sure that would work even better, because you would not have all the convective cooling that would reduce the effectiveness of this hotspot from the sun. So that's a long answer to say no. We have not done that full scale, but I would love to demonstrate that sort of thing. There's a lot of practical challenges to make this work. I don't want to minimize.
Yeah, just that the practical challenge is what I'm interested in solving.
Yeah, exactly. And I think we sort of know what a lot of them are. We just need to be able to know and attack them.
Thank you.
Okay, thanks.
And for JPL. I'd like to comment on something rather than my comment. I'll let you comment on. When we talk about vehicles, we actually have several regimes of operation that require a combination of power and thermal management. So for some folks, we're talking standalone packages that would require the kind of power you need, relatively small, to operate an instrument during the winter night and provide power during the day. It looks like potentially a solar battery system would work for that, but generally speaking, would you comment on how close you think we may be to generic solutions in different regimes in any way? So, the instrument package, monitors sitting on the surface, systems that are rover size, and human stations. Thank you.
I think the way I would respond to that is what has been done. And I don't have an answer for each of those scales. One that I can think of that's applicable is operationally responsive space, and the concept of development of the thermal bus for that.
Between medium to large scale can be made, but the small scale is probably a different solution, thermal solution, which I think is more tangible today than the mid to large scale extensibility question. And I think it's even standardizable, if that's the word, for the small scale capability. Next question?
Hi, Joe Hamilton, Johnson Space Center. Just had a question. With all the solutions available for thermal energy management, should thermal considerations drive, particularly for human space flight, where we pick to land, or can we solve the problem no matter where we pick?
Well, from the robotic standpoint, it's a big cost difference. That's another thing that usually comes into play. We could survive even tonight. Invariably, we have to bring so many batteries with us that there's a thing in the cost cap for proposals. From that standpoint, if the science can be done equally in a more benign environment, costs it's a lot of times.
I think on the human side, on the human class mission side.
So one more comment to that. There's one more ISRU element that is really important here. And that idea that was brought up earlier as with vacuum as a resource. When it comes to thermal control, not having convection be there whether or not you like it, and being able to have high performance solutions that limit and or control radiation and radiation properties gives us a large lever arm that we wouldn't have in a comparable temperature regime on Earth. So that it shortens the complications associated with it. It certainly doesn't solve it. But I think those the existing technologies for insulation, thermal switches, and heat movement and management will allow us to close the thermal balance for clear of the night.
You made me think of something that I think is worth mentioning here. You don't have convection in external spaces, but in a crude environment you would have, of course, air, and it would be part of your thermal management scheme. And one of the things that would have to absolutely be incorporated is the fact that you're at 1/6 gravity, and to the extent that you are using buoyancy as part of your convection scheme, you have to pay a lot of attention to that, because it would be a very different outcome. So that's just a sort of a small comment, and that's just for essentially for crude environments or any enclosed space where you are going to include convective solutions.
If I may, one more comment there. So the one picture I didn't, you guys did, but I did want to point out there was one picture in there that in my talk there at the bottom, that if we didn't have nice participation, I could come back to, but I feel like I need to anyways. One of the last things I wanted to point out in terms of commercial forms is that things are designed to work here, work in a convective environment. I'm glad you bring that up. And we saw earlier the instance of Russian architecture bringing that environment with them. That's something that the Russians have done spectacularly on their own stations. They take things that work, bring them, and they bring the environment with them. And I think that's one of the things that provides a low bar for entry, is just build something that can work here. You're going to pay a mass penalty, but it gets us there. We need to get there to get the experience.
Now?
Yeah. No, you're good. You're good.
Dale Boucher from Deltian. Questions for Kurt. On the thermal wadi, was that sintered or melted material that you laid down for wadi?
The experimental work that we did was it was essentially sintered. We did not push it to the point where we really had molten pools, except occasionally.
Okay.
We didn't really exhaust all of the possibilities here. So, but I will add though that the effectiveness of the, leading to that only 50 centimeter thick slab did require that you really melt it completely and then re-solidify. That's the only way you achieve the improvement in the diffusivity that you would need. Otherwise, it would just have to be bigger, thicker.
And the next question is, to build up that 50 centimeter block, what was your time and energy requirement? How long did it take and how much energy?
We basically gave ourselves the 2 weeks of equatorial lunar day.
So it took you the full 2 weeks to build up that 50 centimeters?
With a very small solar concentrator.
And how big the surface? I'm just trying to get a feeling.
It was not big. I don't remember the dimensions, Dale. I mean, certainly less than a meter square.
Okay, thanks.
Alex Ignazio, Lunar Resources. Kurt, you also remember that Takashi Nakamura, Super Scientific, had 4 concentrators and light pipes, and he ended up melting within a vacuum. small
Yeah,
environment,
that's right.
nothing really regardless, you know, so it's, you know, and we also did similar and made lunar glass out of it.
That's right. I didn't mean to imply that that hasn't been done. What we were seeking to do, Alex, was to do it in a particular way where we would successively build up, you know, layers, you know, in some kind of rastering fashion.
It's a
We just wanted
simple
to
3D
demonstrate the,
Simple 3D printing.
yeah.
Yeah, we did that in Hawaii with solar concentrators.
Yeah, that's right. Yeah, that's right.
Where, Jerry?
Hawaii.
Hawaii.
How'd you get there?
Right on a plane. C-130.
Can you say boondoggle?
Did you say moondoggle?
That's the one. I'm at the pub. So, okay. With regards to thermal management, what is the biggest issue for having continuous operation throughout the night and day in terms of your thermal management? For humans, I'll start off small, all right? For a network, a stationary network, a roving vehicle to go prospecting, and then for a human station. What's the biggest issue that needs to be looked at for that thermal management?
Well, for us, it's the fact that we need to operate both during the day and night is a big driver, having it during diurnal. And it's just the excessive resources that are often needed to tolerate that. Those resources, you know, when I say resources, it may mean that we need nuclear to survive. But given we did have nuclear, I think we could do it.
So it seems to me to sort of push the question a bit further then, that in order for continued survival of the lunar night, we've got to go nuclear. Am I correct in that? Anybody going to argue with me? Jerry?
No,
Oh,
I'm just getting up.
there's a person. Pam's going to argue with me.
I'll argue.
But I want to hear, that's what I'm hearing you say, and I want to make sure that I'm hearing you correctly, because I'm a
Without nuclear, because we're trying to go low
Right.
cost, small motors. And we did close the design of this new heat switch that it provides enough turn down with the types of batteries we're using. That design looks like it's close.
but as a mass penalty.
How
Well,
much?
it's smart size. I think, you know, with the packaging.
Under 15 kilograms.
For what kind of thermal transport?
Yeah, we're talking during the day, we're talking 5 to 10 watts of dissipation during the day. And at night, 1 watt type.
So that's not going to be a prospecting rover then? is it?
Several watts. No, it's not going to be a robot.
Not going to. So I mean, I'm trying to get an idea of the scale of the problem here. Some of the things we talked about this morning were prospecting rovers in a permanently shadowed region. We've got a bit of a thermal issue there, got a bit of a power issue there. I'm trying to understand the limitations and the engineering solutions that are available, because I heard, well, we can engineer a solution, but as long as we've got the mass required, we've got you said money. All right, we'll print some more. Come on now.
Seismic stations could work this way.
Oh, I'm sure they could, but
Yeah.
but it's we got to think, yeah, we got to think permanent. We got to think field station. We got to think enabling other areas. So if we engineer these systems to survive the moon, they're going to survive Mars. We've just reduced risk to going to Mars.
Right.
So all right. So argue with me.
Well, I will say that there is a significant difference in the environment.
I've heard that before. But what about the
Mars
thermal
has
environment?
gas, it is much further from the moon. They're not the same environments.
Right?
So you can't just transplant one from another. But
Why not?
the short answer is convection
Right.
and
Does
energy
that help
density
you?
from the sun.
Doesn't that help you?
It's a great way to get rid of energy if you want to get rid of it.
Right.
But if you need to survive, you want to hold on to energy. Now, of course, it doesn't get as cold on Mars because of that same reason. It's in there holding that energy. So there are trade-offs. But I think you're right in saying it's a good laboratory for going to Mars.
Right.
Once you can develop the operational set off the planet, once you can do your robotics, once you have your power, once you can demonstrate reliability in life, then I think you've got the majority And it's just a shuffling of the thermal problems,
Right.
I think, that brings you.
Right, I mean, that's what I'm getting at. We've got a laboratory in our own back garden. We want to go there to explore. We've got big plans, we've got potentially enabling resources up there that we need to go explore. And we're talking about thermal management here, and I want to know that, you know, let's go do it. All right, what's holding us up? What's the big issue? And so that's what I'm trying to get out of this. So it goes into the report that we can actually make some traction here, make something happen.
Well, we can't help that, so.
You got a great card, brilliant. We'll go to the pub now. But that's where I'm trying to push you a little bit here.
I know not nearly enough about human systems in terms of the thermal management issues that are involved in that to address that. But my sense is from the studies that we did that the smaller the overall device, the easier the problem becomes to solve without using nuclear energy.
Okay.
And so from the standpoint, if you have a array of many small vehicles, there's probably a variety of ways to have them survive and do your prospecting, without nukes. I would say something that I don't think I've heard mentioned very much today at all is that there's been a lot of advances in material science. And so there's a lot of materials that may well be more survivable or more robust in the extreme cold environment.
Right.
Unfortunately, you can't make people out of new materials, so that solution doesn't work for that.
We can wish.
So I think part of the solution is kind of multidisciplinary.
And I think that's the point that needs to be made.
Yes.
That we've got a unique laboratory, and we've got a number of things that we want to achieve. And it needs to be, we need to look at it in multidimensional, multidisciplinary, but we need to give examples of what those different disciplines are.
And I just want to add one more thing to the materials. So Clive, I agree with you with the laboratory concept, but what we can't afford to do is to build, a $1 billion one rover. We need lots of small ones so that some of them can fail.
Yes.
So the ideas didn't work, and we try something else.
Right.
And
We
that's
learn
kind of
from the
where we
failures.
were. That's where we were headed with this thinking, and it's not, doesn't solve everything, but it is an approach. So go ahead.
So Dean Empire Aerospace Corporation spent a lot of time working on EDA issues, and our present way of managing thermal on orbit and on Apollo on the moon involved essentially dumping to the 3-degree Kelvin universe. You can't do that on Mars. So the bliss has to be completely designed, and there's a kicker there, and that is that when you go from 16G to 1/3G, you go from being able to carry just about anything to really being severely weight limited on the back wheel of the crew. So now you, in addition to having to not be able to use your normal stuff, now you got to build a radiator or something that's particularly heavy when you want to have your placement up to the head. So that is one place where you can't just jump from the moon to Mars.
Right. Okay.
Thank you.
No problem. Jerry Sanders. The title of the session is Survive the Lunar Night, or Operate during Lunar Night. However, we saw in the first presentation that during lunar daytime, we have the extreme opposite. During noon, you basically will have a very hard time rejecting heat. And as has been pointed out numerous times, we're talking multiple kilowatts, tens of kilowatts when we have a habitat or a human rover. So when we talk about thermal systems, what are the solutions that you guys see with respect to actually being able to operate under, noon conditions on the moon and get rid of the heat?
So maybe punting the answer, but punting the issue to someone else. But honestly, it's a mass impact. But if you just point your radiators to space, you have your issue solved, right? But I'm punting the issue right now. It's a mechanism issue. It's a dust issue. Still a dust issue, right? I get dust on my radiators. I'm take a penalty on that. But I could do that, right? I could point my radiators if
So
I'm
you
a
have tracking
radiator.
radiators that during the day, you're basically,
Point them to the sky and I'm good to go.
So, you know, if you're talking about your vehicle, you know, you're radiating from the surface to the underside of this vehicle, whatever that, you know, area is, and that's radiating at, you know, 400 Kelvin at you. Are you going to have your radiators either much larger, or are you going to have them radiating at a higher temperature than 400 Kelvin so that you actually can dump the excess heat that you're getting pointed at you?
well,
So it's a big problem.
well, and as you pointed out, the albedo and any hills nearby, if you're perpendicular
I'll
to
get you as well.
the node, you're still
getting the
you're not
influence off the
radiating
other
to
end.
4 Kelvin.
Yep.
Yes, that's right. So very quickly, I had mentioned creating local thermal masses that are continuously radiating without any solar radiation coming on it. So that is a possible cold sink that you can sit on when it gets warm. You know, it's a pina colada. We won't call it a wadi anymore. It's
a pina colada.
So one perspective I want to put on there, we are masters of change. Humans are. When it gets cold, we put on a jacket. When it gets warm, we take it off. I think it's going to be necessary in these thermal controls to be somewhat of a shape-shifting vehicle. Solar shades, etc., things that can morph their thermal capacity.
I think all this discussion is wonderful, and for Claude and for Jerry, it's heard me before many years ago. I used to say there are 3 things you need in space. Number 1, electrical energy. Number 2, electrical energy. Number 3, electrical energy. If you make an energy-rich environment on the moon, you solve your problems. We can do that by making solar cells on the moon and storing that energy in a superconducting magnetic field in the Australian shadow craters or in lava tubes, maybe, all over the moon. So if you have enough energy and have an energy-rich environment, you can solve all of those problems. They no longer become showstoppers.
What's the
And so-
TRL?
But we did thin film growth in the vacuum of space with TRL of 7 or 8. All right, so that's not necessarily a challenge, and we've shown in the laboratory environment all the confidence that can be done that way. Now, let me add, we've also looked at the analysis whereby nuclear or taking solar from the ground and launching it, that's all linear in terms of capacity and cost. By making it there, it becomes exponential. And now you're talking about factors of 10 or factors of 100 cheaper and lower mass by making it there than by taking it up there. All that's possible in the future, but that's one way to look at it. If you've got an energy-rich environment, all these problems become class 1 problems. You know what they are, you know what the solution is. They're not class 3 problems where you know what they are and you don't know what the solution is.
Thank you. I think that concludes the thermal panel. Please give everyone an applause. Thank you.